Hello, the awesome tutor, and today we're going to be looking at bonding. So first, covalent bonding. Now, covalent bonding is to do with the sharing of electrons, because the atoms need to get a full outer energy level, or full outer shell. And covalent bonding occurs between a non-metal and a non-metal. So for example, here we have a hydrogen atom covalently bonded with another hydrogen atom, and we call this a hydrogen molecule, one or more atoms. And here we see that because the hydrogen atom has one electron in the outer shell, it needs one more electron to get a full outer shell. Because if you look at your periodic table, you will see that hydrogen should have one electron in the outer shell. And because it only has one energy level, one shell, it needs only one more electron to complete that energy level, to get a full outer energy level. And so it covalently bonds with another hydrogen atom and shares the electrons with it. So here we have a dot and cross diagram, which you should be able to draw in your exam. One electron from the hydrogen atom and another electron from the hydrogen atom, but they are sharing them, so combined they have two electrons. And so they have a full outer energy level, because it's two electrons in the first energy level, so it's two electrons to complete this energy level. So it's full outer energy level. Now we have the example of an oxygen molecule. Here's an oxygen atom. If you look at your periodic table, you will see that oxygen is in group 6. So it has 6 electrons in the outer shell. And because it's in row 2, it has 2 energy levels, 2 shells. And to get a full outer energy level, it needs 2 more electrons. It needs 2 more electrons to complete that outer energy level. Where is it going to get these 2 electrons from? Well, it's going to get them from another oxygen atom, here, which also needs 2 more electrons to get a full outer energy level. So here we have these 2 oxygen atoms forming an oxygen molecule. Here we have the inner energy level, and here we have the outer energy level. They need to get a full outer energy level, and they need 2 more electrons each. So they need to share 2 electrons between them. So it will look like this. This oxygen atom will share 2 of its electrons, and this oxygen atom will share 2 of its electrons. And then they have that 4 electrons left, because they have 6 electrons in the outer shell, so they must have 6 electrons in the outer shell, but they're sharing 2. So the other 4 is just for them. They're only sharing 2. So as you can see, if you count them up, 1, 2, 3, 4, 5, 6, 7, 8. Because they are now sharing 2 electrons between them, they both have a full outer energy level. 1, 2, 3, 4, 5, 6, 7, 8. This sharing of electrons has allowed to get a full outer energy level. And for the dot and cross diagram, you don't really need the inner energy levels, because in covalent bonding, we're only looking at the outer energy level, the outer shell. So it will look like this. Only the outer energy levels. We don't want anything else. Now let's look at another example. A water molecule. This is a bit more complex because it's got more than 2 atoms involved. Here we have 2 hydrogen atoms, and we know that they have 1 electron in the outer shell. Now for this example, I'm only going to show the electrons in the outer shell because we don't need the electrons in the inner shell. Here we have the oxygen atom, which has 6 electrons in its outer energy level. So it needs 2 electrons to get a full outer energy level, and each of these hydrogen atoms needs 1 more electron to get a full outer energy level. So do you see the link? 1 plus 1 gives you 2. They can share their electrons. So the hydrogen, they can only share 1 between them. So that's why you need 2. And obviously the oxygen will share some of its electrons. And then it will have its 4 left over. So now if you count them up, for the oxygen, 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons outer shell, full outer shell. The hydrogens, 1, 2, 1, 2. Each of them have a full outer shell. So what we see here is that this sharing of electrons is very important for covalent bonding. And because the oxygen only needs 2 and the hydrogen needs 1, it's fairly self-explanatory to figure out how they share their electrons. Okay, for the hydrogen it's really easy because it can only share 1 electron, so remember that in your exam. And then the oxygen needs 2 because one hydrogen can only share 1, you need 2 of them in order to share 2 to get the oxygen to a full outer shell. Now obviously these need 1, so you get 1 each from the oxygen. So simple covalent molecules. These are the molecules that we've been looking at. Water, oxygen, hydrogen, and here we have ammonia and methane. They don't have that many atoms. Their molecules are small, they're simple. So consider this. Here we have molecules which are covalently bonded. So they have fairly strong covalent bonds between each atom. But between each molecule, this is what we call an intermolecular force. Intermolecular force of attraction. And for simple covalent molecules, this intermolecular force of attraction is very weak. And this intermolecular force is the force you overcome when boiling a liquid. And so this is why simple covalent molecules have a low boiling and melting point, because of the weak intermolecular forces, which are easily overcome. And so we see here that simple covalent molecules that are very small have weak intermolecular forces, but the bigger the molecule, the stronger the physical force of attraction between them. So if we take diamond for example, that's a giant covalent molecule, and it has a high boiling and melting point. But simple covalent molecules, they have low boiling and melting points because of the weak intermolecular forces which can be easily overcome. And so the bigger the molecule, the bigger and stronger the physical force of attraction between them. So if we look at a very common question, why does blah 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 have a low melting and boiling point? Considering this is a simple covalent molecule, like a hydrogen molecule or a water molecule, it's all to do with the intermolecular force of attraction, nothing else. And because this intermolecular force of attraction between the molecules is very weak, it requires only little energy to overcome. So that's why it has a low melting and boiling point. These are your 3 marks. It's a generic answer. Okay, so now let's look at ionic bonding. Now, unlike covalent bonding, ionic bonding takes place between a metal and a non-metal. Now first of all, what is an ion? An ion is a charged particle. So for example here, we have a chloride ion, an oxide ion, and a hydrogen ion. So they are charged, positively or negatively charged. And the thing about ionic bonding, when you have a metal and non-metal, because they ionically bond, the metal is the one that loses the electron, always, so it becomes positive. Why? Well, we know that an atom has overall no charge and consists of protons, neutrons, and electrons. And the reason it has no charge is because the number of protons is equal to the number of electrons. Protons have a charge of +1, electrons have a charge of -1. So they cancel each other out. So the number of protons is equal to the number of electrons. But if the metal loses some electrons, then now you will have more protons than electrons. So overall to become positively charged. And then the non-metal is the one that gains the electrons, so it becomes negatively charged. Because if you gain more electrons, then you'll have more electrons than protons, so you'll have an overall negative charge because electrons are negatively charged. So this example we have sodium and fluorine. I only drew the outer energy levels, the electronic structure of the outer energy levels, because we don't need the inner energy levels in this case. So, like covalent bonding, these atoms need to get a full outer energy level because that makes them more stable. And because sodium is in group 1, it has 1 electron in the outer shell, and it needs to either gain 7 electrons or lose 1 electron to get the full outer shell. And for fluorine, it is in group 7, so it has 7 electrons in the outer shell. It needs to either gain 1 electron or lose 7 electrons to get a full outer energy level. But what's easier? Losing 7 electrons or gaining 1 electron? Gaining 7 electrons or losing 1 electron? Obviously it's losing 1 electron and gaining 1 electron. So if this metal loses 1 electron and this non-metal has to gain an electron, do you see the link here? This electron, when it is lost, will go to the fluorine atom, and now that fluorine atom has that electron from the sodium. Now they both have full outer shells because obviously the next inner energy level of the sodium is already full, so now has a full outer energy level, and this also has a full outer energy level. And here we have what you need to know, how to draw like the structures. So if you want, you could draw all the energy levels of the sodium and show that they're full outer energy level. But because you've lost that electron, that outer energy level is no longer a proper outer energy level, so you look at the next inner energy level. I'm not going to draw that in this case. For the fluorine, it has gained that electron, so let's draw it. It has 7 electrons of its own, and 1 electron it gained from the sodium. Because it now has 1 more electron than protons in its structure, because an atom has no overall charge, but now it's an ion because it has 1 more electron than protons, so it is overall negatively charged. So by how much? By 1. So it has 1 minus charge because it has 1 more electron, and electrons are negatively charged. Now for the sodium, it has lost that electron, and so now it has more protons than electrons. Because it lost 1 electron, it now has 1 more proton than there is electrons, so it has an overall charge of 1 plus. Here we have magnesium, which has 2 electrons in the outer shell, and we have oxygen. This is not an energy level, it's just an O representing oxygen, which has 6 electrons in the outer shell. Magnesium needs to lose 2, oxygen needs to gain 2. So obviously, these 2 electrons will be lost by the magnesium, giving it a full outer shell, and gained by the oxygen, giving it a full outer shell. So let's look here. We have 2 electrons from the magnesium, and the other 6 electrons are its own. Now it has 2 more electrons than there is protons. And because electrons are negatively charged, its overall charge will be 2 minus. 2 more electrons, 2 more negative charges. So this is now an ion, remember. And for magnesium, it has lost 2 electrons So now it has 2 more protons than there is electrons. So its charge is 2 plus, because 1 proton has a charge of plus 1. So now let's look a bit deeper into the ionic compound that is formed. In this case, we're going to look at the example of sodium chloride. So we have a sodium atom and a chlorine atom. Sodium, 1 electron in the outer shell. Chlorine, 7 electrons in the outer shell. So this electron will go here. Sodium loses it, chlorine gains it. And so for the sodium, it will now have a positive 1 charge because it lost an electron. For the chlorine, it will have a 1 minus charge because now it has 1 more electron than there is protons. Okay, so 7 electrons from itself, 7 protons, 7 electrons, no overall charge, but now it has 1 more electron. So 1 more electron than protons, a 1 minus charge. And the thing about ionic compounds is their melting points and boiling points are high. And this is because of the electrostatic forces of attraction between the ions. And they are strong electrostatic forces of attraction. And all ionic compounds are a giant lattice of ions, as you see here. Now this structure I've drawn is not very accurate. Okay, the ions are not even in the right place, but you get the idea. A giant lattice, and it's 3-dimensional. Ions and ions. Strong electrostatic forces of attraction. The thing about ionic compounds is they can conduct electricity, but only when they are molten, so a liquid, in their liquid form, or in solution, dissolved in water. And then this is because when they are molten or in solution, the ions can move. And so they can carry that charge, which allows electricity to be conducted. So the melting and boiling points, we said, are high. And this is because the electrostatic forces of attraction are strong, which require a lot of energy to overcome. This has been the Awesome Tutor. Bye.